All right, so today we're looking at 3.8, section 8 of chapter 3, where we're looking at all those derivatives and all those rules, and we're looking at the derivatives specifically today of inverse trig functions. Now, the first thing we're going to look at is the derivative of a basic inverse. So if we had f of x is equal to x squared, that means that df dx, the derivative of f of x with respect to x, would be 2x. So at x equals 2, we would have a slope of plugging in 2 times 2. The function would have a point at 4, but it would also have a slope of 4. So the slope of the tangent line at the point 2, 4 would also be 4. Now, if we did the inverse of this thing, if you remember how to find the inverse, you're going to think of this as y equals x squared. You're going to swap your x and your y, and then you're going to solve for the new y. So you end up, and this guy does it just a little different. Well, no, he doesn't. So you end up with y equals the square root of x. So my function, my inverse of the function, is the square root of x. So there's the graph of it. Now remember, with an inverse, the corresponding point on the inverse of the point 2, 4 is switching the x and the y, so it's at 4, 2. So to find the derivative of the inverse function, we take the derivative of this, and we end up with 1/2 x to the negative 1/2 power, or 1 over 2 times the square root of x. So there's the slope at that corresponding point on the other problem. Now at x equals 4, we know that we're going to get 2. That's the corresponding point. Remember, all an inverse does is undo it. So if you put 2 into our function to get 4, then you would put 4 into the inverse function to get 2 back. So the domain and the range with inverses swap places. The x's and the y's swap places. So at the point 4, 2, if we calculate what this would be, we're going to end up finding that it's 1/4. Well, it's not a coincidence that it is the reciprocal of the slope over here. So the slope at 2, 4 on the original function is 4, and the slope on the flipped point, 4, 2, on the inverse function is 1/4. Notice they are not negative reciprocals, and notice that these tangent lines do not intersect at a perpendicular angle. They are just simply reciprocals of one another. So because x and y are reversed to find the reciprocal function, the following pattern always holds. The derivative of the inverse with respect to x at f of a is equal to 1 over the derivative of f of x at x equals a. Now remember what your notation is here. F of a is just another way of saying y. So this is where x equals the actual y value from the original part. And this is where x is equal to a, which was the original x at your point. So make sure you get these straight. Now another way that you can look at this, and this is the way I do it. I honestly do not remember this formula specifically, but what I think of two functions that are inverses, f and g. And if we do a composite of two functions that are inverses, we're always supposed to get x. So if I differentiate this, what I'm going to get is f prime of g of x times g prime of x equals 1. So if I want to find the derivative of the inverse, well, it's right here. So all I got to do is get that all by itself, so I can divide by f prime of g of x. So g prime of x is equal to 1 over f prime of g of x. And that's how you would find it. So that's another way. That's the way that I actually work it out. And remember, I differentiate this each time I have to deal with the derivative of an inverse. All right, now a typical problem using this formula might look like this. We're given f of 3 equals 5, and df of x at 3 is 6. Find the inverse, the derivative of the inverse function at 5. Well, using that formula we were just looking at, remember that the derivative of the inverse with respect to x evaluated at x equals f of a, or in this case f of 3, which by the way f of 3 is 5, is equal to 1 over df dx evaluated when x equals a. So that means, using this into this situation right here, that means that df inverse of dx when x equals 5 is equal to 1 over df dx when x equals 3. So now, what is the derivative with respect to x when x equals 3? Well, it's 6. So that means that this thing is 1/6. Now, let's use implicit differentiation to find the derivative with respect to x of the inverse sine of x. Now remember, this is not 1 over sine. This is the inverse function of sine. Remember, this is what we use when we want to find the angle from a sine value. If we have a value like the square root of 3 over 2, we take the inverse sine of it. That tells us what angle that sine value applies to or is found at. So be careful and don't mistake this for 1 over sine. That's not what it is. All right, so if we have y equals inverse sine of x, what we can do is we can use implicit differentiation here. And first thing we're going to do is we're going to take the sine of both sides. The sine of y is equal to the sine of the inverse sine of x. Well, the sine of the inverse sine of x would just be 1. Or sorry, x. So then we can implicitly differentiate both sides. That means that if we take the derivative of this one, this side over here with respect to x, we're going to have to include a dy dx. So we're going to end up with cosine y dy dx. And the derivative with respect to x of x over here is just going to be 1. So that means that dy dx equals 1 over cosine y. All right, there's only one problem here. So we found what dy dx is of the inverse sine of x, but we're finding it with a y in it. We don't want a y in it. We want to find some way where we can express dy dx in terms of x. Now, from this point on, guys, I'm going to be honest, you don't have to know how to do this, but I do want you to write it down and put it in your notes so that it's there so you can look at it and see how some of this stuff was derived. So we're going to use the Pythagorean identity, sine squared y plus cosine squared y equals 1. Normally we see this with sine squared x, cosine squared x equals 1, or theta. It doesn't matter, whatever variable. If we do the sine squared of y plus the cosine squared of y, it equals 1. If we do the sine squared y of anything plus the cosine squared y of that same thing, it equals 1 every time. So that is an identity that always works as long as we put the same variable in, or the same value in both places. All right, so now we're going to solve for cosine squared y. We end up with 1 minus sine squared y is equal to cosine squared y. Then we can actually take the square root of both sides. So cosine y is going to equal plus or minus the square root of 1 minus sine squared y. Now, we're limiting our y value between negative pi over 2 and pi over 2. Well, you're probably asking, well, why are we doing that? Well, we're doing that because the inverse sine will only find angles between negative pi over 2 and pi over 2. That's the limitation that we have to have so the inverse function is actually still a function. So that means, and we know over that interval, the cosine of that y value will have to be positive. That's in quadrants 1 and 2. And cosine, the x value, is always positive in those two. So we can get rid of the minus part. So it's only the positive square root. So therefore, the cosine of y is the square root of 1 minus sine squared y. So we can put that in place of this right here. All right, and then we look here and we're saying, okay, well, sine squared y, we still have a y, so we really haven't done anything, but there's only one thing that we have left. What is sine y? Well, if we look right here, sine y is equal to x. So in place of having sine squared y, we can just have x squared. So the derivative with respect to x of the inverse sine of x is 1 over the square root of 1 minus x squared. So we've just derived the formula for the derivative of the inverse sine using some implicit differentiation and a Pythagorean identity, but you can do these things if you feel a little creative. Like I said, you're not going to have to do this ever on a test, but it's good to see how you can actually do these things if it comes down to the point that you actually need to. All right, now we could use the same technique to find the derivative with respect to x of the inverse tangent of x and the inverse secant of x. We're not going to do that. I'm just going to show you what they are. Here are the derivatives of the inverse sine, which we just derived. This is including the chain rule. If we have some function u here that's squared, we have to multiply by the derivative of that function with respect to x. All right, and then here's the derivative with respect to x of the inverse tangent of u. Once again, using the chain rule. And then here's the derivative with respect to x of inverse secant of u. Now, notice the absolute value here. If this u is something that is always going to be positive, you can drop the absolute value. Otherwise, you have to have it there. For instance, if this was the inverse secant of, for instance, x squared, well, when you put x squared in here, all this is a formula you're just plugging all the stuff into. So once you put x squared in here, well, x squared is always going to be positive, so you can drop the absolute values. That's the case. Now, you may or may not hear or see these things referred to as the arc sine or the arc tangent or the arc secant. Those are the same thing. The arc sine of x is equal to the inverse sine of x. These are the same thing. They're just two different ways that they refer to them. So don't freak out if you see arc sine or if I refer to it as arc sine. Sometimes I will. All right, now what we're going to do is we're going to use some identities about inverse sine and inverse tangent and inverse secant to figure out what the derivative of the inverse cosine, inverse cotangent, and inverse cosecant are. Well, we have an identity that says the inverse cosine of x is pi over 2 minus the inverse sine of x. So think about this for just a second. If you take this and you differentiate both sides, well, this side over here is what you're really worried about because you're trying to find out what the derivative of this is. So what you would have is you would have d dx. And what happens when you take the derivative of pi over 2? Well, remember, pi over 2 is a constant, so that's going to be a big fat 0. And what's the derivative of inverse sine of x? Well, you found it to be this right here. So this is 0 minus 1 over the square root of 1 minus u squared, or in this case x squared, since it's got x there, x squared, and then times the derivative of x, which would be 1. So you just get negative of what you have right here. And that's exactly what we deal with. So the derivative with respect to x of cosine, or the inverse cosine of u, is negative 1 over the square root of 1 minus u squared times du dx. So from sine to cosine, all we do is we throw a negative out in front of it. Now, we also have a similar expression, or a similar property, for cotangent, relationship between cotangent, arccotangent and arctangent. Once again, 0 and minus is just going to make the derivative of the inverse cotangent the negative of the derivative of the inverse tangent. So negative of this thing over here. And last but not least, we have the same relationship with inverse secant and inverse cosecant. Pi over 2 minus inverse secant is equal to inverse cosecant. So when we take the derivative, we got 0 minus the derivative of secant, of inverse secant, so we end up with just negative of this thing right here. Now, here's a little memory tool. Whoops, sorry. What do we know about every single one over here? They all start with c. So the derivative of any of the inverse c functions, c trig functions, are going to be have negative out front. The ones that don't start with c do not. That's just a little way to remember and keep yourself from making a mistake of forgetting these minuses out in front. Any of the inverse trig functions that start with c, you're going to put a minus in front of it. All right, now your calculator contains all 6 inverse trig functions. However, it is occasionally still useful to know the following. That the inverse secant of x is the inverse cosine of 1 over x. Guys, don't worry about these. Don't worry about writing those down or anything. I have not ever, I can't think of a time when I've actually used those on any of the AP material. And if you have to use something like that, they'll typically give it to you. All right, that's all of 3/8.